Welcome to another particular software webinar, DIY Async Message Pump, Lessons from the Trenches. Our presenter today will be Daniel Marbach. He is a pro at message pump design and async await. Whenever I have a problem with async await anything, Daniel's always the guy I turn to. So I guess now we'll turn it over to you, Daniel.
Hi David, so thanks for the introduction. Hi everyone. So if there is anything wrong with my sound or something like that, please feel free to shout out in the Q&A section and David will kindly nudge me so that I speak up a little bit, slow down or whatever you want me to improve here. So, well, before I joined Particular, I was working for a small company in Switzerland. We were building a medical patient record kind of system that was hosting patient records for over 4 million patients in Switzerland. And well, this system was focused only on like medical patient records, and once upon a time someone in there had an idea. So basically the business analyst or the stakeholder came to us and said, hey, since we're already doing kind of medical invoicing, wouldn't it be cool if we could do any kind of general purpose invoicing? That sounds nice. So we said, well, I don't know, we'll see. And you know it, right? That's how systems evolve. So we tried to shoehorn whatever we could on top of that medical invoicing records that we had in the database. So one thing that we did is, this is the architecture diagram that we basically had. So we had a legacy system. It was built 13 years ago. It was still using ADU.NET transactions and stuff. And we had some WCF services in the front end in the demilitarized zone that was trying to deal with the invoices and invoice refund queries and commands that came in. Because at that time RPC was the thing to be used, we used that RPC style. So whenever a request came in, we actually issued queries or refunds against the Windows services in the backend, and those Windows services did read and writes with ADU.NET 1.1 against the storage layer, which happened to be a SQL cluster. One thing that we didn't really realize was that once we moved from medical invoicing to, let's say, general purpose invoicing and invoice refunds, and we opened up this system to any kind of web shops out there, we essentially lost our maintenance window. Because, well, web shops are open all the time. They're open 24 hours, right? When you're sitting at home, you want to buy something for your significant others, you don't want to wait until that web shop is open. It's always open. You can order stuff and the invoicing happens behind the scenes. So what we also realized is that once we opened up our front-end services to these WooCommerce PHP clients, what we realized, it seems that in that area that PHP developers think that whenever they want to speed up the backend processing of those invoice refunds and invoice processing, they just started hammering and pulling us more and more and more. So, well, this was really a huge problem because, well, the storage layer wasn't really capable of coping with the load. So what we had here was, we essentially had the RPC call stack of doom. Well, because of the whole RPC call chain, whenever there was some latency in the storage layer, or when we had to do maintenance on the storage layer on our SQL Server cluster, which happened to be using a pretty old and rusty version of SQL Server, those latency effects and problems basically rippled through the whole call stack up to the front-end layer. So what it means is that requests somehow stalled, they somehow took longer, and sometimes they even like completely stopped for multiple seconds, and sometimes they threw exceptions, which obviously some genius developer caught on the front-end service, but they didn't really bubble up to the users. But for the users of those web services, it was sometimes pretty much impossible to actually send in queries or invoice refunds. So what we can say with that architecture that I showed you before, we had a huge temporal and spatial coupling that was horrible to handle. So we couldn't really fulfill the SLAs in that architectures, and orders got lost, invoice refunds got lost, and we couldn't really throttle it when we had to do maintenance, because every request that came in had to be handled by the backend service. There was no other way around it. And one thing that we also realized was it was pretty difficult to troubleshoot this monstrosity, because when something went wrong, we could only actually see the invoice refund queries or the invoice refund commands somewhere in the WCF call stack or exception log. So that was pretty horrible. But then we said, how could we solve this? And we realized, well, invoice refunds, for example, or invoicing is actually a pretty good domain that we can pack every data that we get from the customer or from the clients that call those APIs. We can pack it into a command and we can send it to the backend. So we realized we should praise the lords of messaging, and we should try to adopt a more fire and forget approach in this architecture based on messaging. So we then went back to the drawing board and realized and started having a discussions how we can essentially tweak this architecture I showed you before a little bit to make it a bit smarter. So what we came up with was the following. So we didn't want to touch everything, you know it, right? Legacy systems. The code was sometimes 13 years old. You don't want to go in and change everything, the whole call stack, because that's going to blow up in your face. So we did really, really small changes. So what we did is on the WCF services front end, we essentially introduced some kind of a query cache. And then we introduced a messaging cluster in between. At that time, we were using MSMQ, but that doesn't really matter. So whenever a refund came in for an invoice, we essentially issued a command, invoice refund, to that queue, and the backend system, instead of being queried or called via RPC directly, was just listening on those queues and essentially fetching those invoice refund commands, doing some processing against the storage, and once it was done, then published an invoice refunded event in that specific example that was subscribed by the demilitarized zone, and then the front-end cache could be updated. So the good thing was the PHP client could hammer us as much as they wanted, because we were always serving the queries for the state of an invoice refund from that front-end cache. Everything was decoupled, especially from a temporal perspective. We had some good and pretty awesome scaling vectors in this architecture, because we could essentially just spin up another backend instance that was also fetching stuff from the queue. We could throttle things. We could basically deterministically say how much a given backend instance can handle, and then just pull out as many messages out of the queue as the backend instance was able to handle. We had retries. For example, when the storage layer was choking and we had timeout exception, we could just retry those messages. And what was also pretty cool, we had basically intent capturing requests as messages, and a pretty reactive kind of architecture. So that was all nice, and we were fully bought after this initial architecture proposal, fully bought into the messaging world. But then we had a hard decision to face. So what we essentially started talking about was, well, should we build kind of a messaging library ourselves, or should we buy something or use something that is there out of the box? Well, in this project I talked about, we actually bought something out of the box, but in another project there was also, we didn't. And we thought in that other project, well, after all, building a messaging library is not really complex. How hard could it be, right? Famous last words. So I want to walk you through in this webinar through some of the challenges that we've faced building a robust messaging library. And before I do that, we have to talk a little bit about the basic features that we need in a messaging library. So let's go back to that architecture diagram. So on the front-end services, we have to have something that is sending messages, so basically capturing the business intent, package it into some kind of a message payload together with headers, and then shuffle it to the destination queue. And then on the backend part, we have to have something that is receiving messages out of the queue and potentially publishing or sending other messages back to other queues, or publishing messages again to the front-end parts. So that seems to be pretty simple. Let's have a look at some code. So I'll show you now the first infrastructure piece, or the first attempt that we came up with. So this is the code that we initially wrote. So so we had a cancellation token source, and that cancellation token was responsible to cancel on, when we shut down the system, the whole message pump. Here I'm doing this after 5 seconds. Then we had a cancellation token that we could constantly poll. We had a loop, which is basically a while loop that we shovel off onto the worker thread pool by using task.run. Inside that while loop, we do something like we read the messages that are in the queue. We get the payload and the headers. And that is some raw byte information. Here I'm using memory of byte and also another memory of byte for the headers. And then we deserialize the payload and the headers into something logical, which can be, for example, if we have a JSON payload in the queue, could be a class. And then once we have that class, we then essentially call the business logic. That business logic is here that handle message. We hand that message over to that business logic. We do something with the message. For example, we eat up a little bit of time. Here I'm simulating this with task delay for 1 second. And then we continue polling stuff from that queue. And once we are done, we await until the whole loop is canceled, and then we dispose all our resources. So that's pretty much the asynchronous code that we wrote at that time. And by the way, I'm showing here a polling implementation of a queuing system. So some more advanced queuing system might support some kind of a push-based or more reactive kind of approach where we have some kind of observables that we can subscribe to, so that whenever is something on the queue, then stuff automatically trickles into our code that is subscribing on it. I think it doesn't really matter whether it's a polling kind of implementation or a push-based implementation. At the end of the day, you end up having some kind of code that might get data, deserialize data, read from the queues, and execute the actual business logic. And at some point, you want to shut it down. So the only difference would be that you have in the polling infrastructure, you have a while loop that pulls stuff from the queue and some additional delays and stuff to actually not overwhelm the code. So let's go back on what we just saw. So I showed you before in the previous diagram, I showed you that there is also a sending part, and I did not really talk about the sending part in the code I showed you before, but I think that sending messages to a queuing system is pretty simple, right? So what we can imagine us doing is we essentially take a message that is a logical an instance of a class. We take all that data, we serialize it to some kind of payload and headers again, and then we just send it to the queue. And that's pretty straightforward, I think. So let's go back and let's do a little bit of a brief recap of what we just saw. So with a little bit of task parallel, library hand waving, and some cooperative task cancellation 101 and some async magic, we actually have been able to write a pretty robust and solid infrastructure that fetches messages from an existing queuing system. So this worked pretty nicely, so we shipped it into production, and it worked until someday, well, one of the small web shops that we had actually got some kind of a precious item that was loved by a lot of customers. And suddenly, a lot of customers started buying this stuff and started buying like crazy. So essentially, rush hour happened. And normally, rush hour is a great thing, right? Because you're actually selling more products. That's nice. Well, let me show you what happened in our case with the code I just showed you before. So what happened in that code was whenever a message came in, we handled it, executed the business code. When that message processing took 20 seconds, nothing was happening at all during those 20 seconds. So then after the code was done, it picked up the next message, and it picked up the next message. So what we can say is that it was processing one message at a time. Why is that a problem? Well, if you have heard, maybe you have heard about the critical time. What you can say is the critical time for that queue that we were consuming from went through the rooftop. The critical time is defined as the time that it takes to actually process a message, but the critical time does not only involve the processing time of the code that is being executed, it starts counting once the message is in the queue. So what we can say is once a message is in the queue, the critical time starts counting. So it's the network send time that it takes to actually send the message into the queue, then the queue wait time until our pump actually picks it up, and then plus the processing time of our handlers. And that critical time, although we didn't know that at that time, was basically increasing the more load we had on our system. So we can address that easily. We said, that's easy, we are developers, we can fix stuff like that. So we put back our sleeves and got some coding done. So we said, well, concurrent programming is kind of a scary beast, but I think we can manage it. So we added a little bit of concurrency into the previous code. Let me show you in a quick demo what the previous code actually did to not only illustrate it with slides, but also here with this code. So I'm now letting run the first version. So as we can see here on my screen is we're executing the pump, and whenever something was handled, we then take the next message out of the queue, takes the next message out of the queue. So that was the code that I showed you before. Then what we said was, well, we know async, we know concurrency, and we want to process things as fast as we can, as fast as possible. So we did just a tiny little change. So what we did is, instead of directly awaiting the method that fetches stuff from the queue and deserializes stuff and executes the business logic, we wrapped it in a fire and forget. Fire and forget is nothing more than just not writing the await statement here on this line. Right? So by not writing the await statement, we do not sequentialize this code, and we just execute this TPL code here in the background, and we continue processing messages. Let me go back to the slides and do a brief recap. Well, because we thought, well, this is just a tiny little change. We just introduced fire and forget, which is reasonably simple. We don't need to do extensive quality assurance or testing of this code. We can like pair review it on a pull request and just send it in and ship it to production. And this worked quite nice. It was super awesome. We didn't see any problems until, well, again, this freaking damn rush hour happened. Well, if only we wouldn't be making so much money on our systems, life would be so much easier as developers, wouldn't it be? Oh, wait, actually, we're losing money right now. Well, how can that be? Well, what we can say with the tiny little code change is the pump now runs in an unbounded concurrency mode. So, well, what it does is, in theory, it starts, the more messages we have in the queue, the more it starts fetching those messages concurrently from the queue and executing our business logic without any limitations. But without any limitations is actually a lie. Every code that we write in production usually has some kind of limitations, some non-functional requirements attached to it, but also limitations of hardware and resources that we are using. In our case, it was the database behind the scenes, right? Because every code that is executed in a massive concurrent fashion executes queries and inserts against the database. At some point in time, we might be depleting the connection pool resources of the database, and we start overloading the database, or here the ADO.NET connection drivers. And once that happens, well, we start seeing timeout exceptions, DB connection pool exhausted warnings and stuff like that. So once that happens, what we can say is we actually lose the whole benefits of why we introduced the storage-based queues in the first place. remember, when I showed you the first architectural drawing, we could have done that entirely with queues in memory, some kind of concurrent dictionary or concurrent queue infrastructure kind of thing, and do everything in memory. But we did not do that because what we have with a messaging implementation is we can essentially offload all the requests that are coming in from our clients onto some file-backed queues. And because it's file-backed, we have a better scaling vectors in our architecture. But once we start consuming messages like shown here on this slide in an unbounded concurrency way, all bets are off, right? Because things start falling and we start essentially overwhelming the weakest link in the chain. So, well, the best thing if we could introduce something is that we would essentially do some analysis on our weakest link in the chain or our weakest element. In our case, it was the database and the database connection pool. Yes, you can always increase the database connection pool, but even that has some limitations. So what we said is, well, how about we leave it around 100 connections, because we knew that was the case with SQL Server at that time. So wouldn't it be nice if we could essentially limit the amount of concurrency to 100 messages at the same time that we are handling once we have a lot of messages in the queue? And we started implementing that, and I'm showing you that in a second. But before I show you that, I want to do a brief demo of the unbounded concurrency so that you actually believe me. So what I'm going to do is I'm going to run the code with the Fireandforget here on this machine for I think 200 milliseconds. So as you can see here, this code runs runs almost forever. So even on this machine, I think I have 24 cores. I can see that we were able to essentially pump 134,000 messages through that unbounded concurrency code in just about 200 milliseconds execution time. That's pretty insane, and that every code that we would have in the background would essentially be completely overwhelmed. So how did we achieve concurrency limitation? Well, in the .NET framework there is something called a semaphore, or the newer version of it is the semaphore slim. Semaphore is basically like a toll lane on a highway. So if we have an 8-lane highway and we have a toll lane that spreads all over those 8 lanes, we could say when a semaphore has also 8 slots, only 8 cars can pass that toll lane. If we had 8 lanes on the highway, but we only have, the toll lane only has 6 places for cars to pass through, then we would essentially limit the concurrency on the semaphore example to 6. So what it means is only 6 concurrent things can enter that critical region, or going back to our toll lane example, only 6 cars out of 8 lanes could pass through the toll lane. So we create that infrastructure, and by the way, the semaphore slim is the one that actually allows you to call wait async and doesn't provide a blocking way, which is kind of, well, it provides a blocking way, but this is the more async enabled API that also accepts a cancellation token. So what we do is, before we essentially Fireandforget the fetch handling stuff from the queue, we acquire the semaphore. So if we still have slots available, then this code will just fall through, and then it will execute the business logic, and then inside the business logic, once we are done with executing the business logic, we release the semaphore and make more slots available again in the semaphore. It's basically like a car is passing through the toll lane. This is the release. And well, we had to make a few other changes. We also figured that potentially we don't want to just completely abort while we are processing things. We also wanted to gracefully shut down. So what we did is we used the semaphore that we had in place, and we checked it in a while loop until all the slots were available again, so that we knew that we did not abort in the middle of processing messages. So that's the code here. And by the way, if it's going a little bit fast, don't worry. at the end of this webinar, I will share a link to a repository on GitHub that contains all that code, and you can execute that code on your machine as well, and also debug through the code if you're interested to dig deeper. So that's the changes that we made. Let me go back to the slide and do a brief recap. So, well, with that semaphore in place, we could essentially control the floodgate that was coming into our code. So we could limit it to 100 concurrent calls. So we did never use more than 100 connections for a single endpoint going against the SQL Server, which was kind of nice, and we had better control over the runtime behavior of what the pump was doing. So that worked pretty nice. And it worked for multiple months. That was not an issue. So, but what we kind of realized at that time, well, I was building that abstraction, that messaging abstraction. That was a really fun exercise. I mean, at that time, it was pretty cool when I could distract myself with writing infrastructure code instead of needing to fiddle with those damn business requirements that came in from our business stakeholders. And I had this Mercedes-Benz in mind, but you know it, right? Well, I was the team lead at that time, or the technical team lead who originally built that abstraction, but while time was progressing, I did not really have time to maintain things anymore. So the team started essentially extending the code I wrote under pressure. I know what you're thinking. He's going to blame the team. And actually, yeah, I think I could blame the team. No, I'm just kidding. It's not the team's fault. Obviously, we all own the code together in a good team, and it would be too easy to just blame the code. I mean, it's natural that when you have infrastructure code, the business doesn't really care about the infrastructure bits and pieces. It mostly cares about the implemented business requirements, and everything else is just an implementation detail. Well, what we also saw is that we had some internal or technical requirements for audit purposes, but also we wanted to add a bit more flexibility to that messaging middleware that we were building. So for example, we said, well, whenever a message comes in that we handle successfully, we want to audit something, whether it's going to be a log statement, whether it's going to be something that we insert into a database. So this is kind of a cross-cutting concern. But we also realized that potentially we want to be a bit more extensible in terms of adding different behaviors that we can configure during runtime, or at least during code time, into that kind of pipeline that we were building. So what I'm going to show you now in code is how the pump actually really looked like that we were building over time. So the pump roughly looked like this. As you can see here, this code is still pretty similar, pretty familiar. We have the concurrency limitation of that code. And we have the graceful shutdown. But what happened here is, well, we realized potentially we need some kind of transaction that is wrapping the code that is fetching stuff from the queue. So we created some kind of a transaction, whether it was the native transaction of that time of the SDK that we were using, or whether it was some kind of a transaction scope, doesn't really matter. Then inside that transaction scope, we realized, well, we want to execute code that has a lifetime that is bound to something that is coupled to a message that is being handled. So you probably know that from ASP.NET or ASP.NET MVC or Web API, they have the concept of a child service provider. So whenever a new message comes in, we want to create instances that live for the lifetime of a message handling, and then at the end we want to get rid of all those instances. So we wrote a kind of a child service provider abstraction kind of thing. And then what we also realized is that, well, that to be able to implement those cross-cutting concerns, we need to kind of have a higher level abstraction that allows us to plug in flexible middleware into that whole execution pipeline. So instead of directly handling the business logic in here, we essentially came up with this func handler context, task array of multiple middleware implementations. I know probably your head is currently exploding right now while you're eating your lunch, but this is how our code looked like. And then we executed the middleware. Once the middleware was done, successfully completed, we completed the transaction. When something was happening, an exception, we didn't really know what to do, so we had some to-dos in there, some comments. We figured we will address problems like that later, and obviously at some point we need to release everything. And I'm showing you an example here of such a middleware. So the middleware, for example, did resolve our message handling abstraction from some child container, and then it executed all those handlers with the message that was provided. And then at that point in time, suddenly our code looked like this. We had a message handler class implementation that implemented that I handle messages of T, that got a message that could do the actual business logic. And by getting access to some kind of infrastructure that was also provided by this middleware, we could then send out messages to multiple queues or publish events back to the demilitarized zone that I showed you. So this is the code that we came up with. And by the way, I forgot to show you the previous concurrency limiting example. So let me briefly show you that so that you actually believe me that the semaphore actually limits concurrency. So as we can see here, we're now executing the pump that we with a semaphore with a limited concurrency, and we limited the concurrency here to 3. So what we saw is that we are only executing concurrently three message handling pipelines at the same time. So that is the benefit of the semaphore. And again, this is potentially how the code looked like that we have built over time. So going back to the slides. So, well, over time, while we were evolving this code and we didn't really actually write middleware and infrastructure pieces, depending who you ask, we essentially, instead of having a Mercedes-Benz, we actually built something like this old and rusty car. But it really depended who you asked. There's some people in my team were really like excited about this infrastructure piece. So for them, and some weren't really excited. So for those who really weren't excited, it looked potentially the middleware looked like this. And by the way, this happens when you're preparing a talk and you Google funny cars. This is what images you get when you do that, when you're procrastinating over preparing a talk. Well, for some people it looked like this, and for some other people that really, really liked the code and were super enthusiastic, well, the code potentially really looked like this. So I don't even know how you can come up with such a car, but it looks like the guy is really enjoying himself with potentially his girlfriend in this car. Anyway, I'm getting off topic here. So, but then what we just showed here, we actually just showed the basic bits, right? We talked about sending messages, we talked about receiving messages. I briefly, in the last code example, I showed you some kind of a transaction abstraction. In order to have some robust and reliable code out there in production, we have to have a deeper look at how transactions actually work, and we have to think about transactions. So, well, what we can say is code that is being executed under a message that is being handled is never side effect free, right? So we will always, as part of the code, we will always do something. For example, let's look at the pump. So once we want to pump something out of the queue, we essentially start a transaction, and then we fetch a message out of the queue, and then we execute this code. But because the code is not side effect free, we might end up sending out messages to multiple destinations because we want to publish messages. We want to send, I don't know, something to Salesforce or something to some web service. We want to do that in a reliable way. So the more we bought we are bought into this messaging world and fire and forget kind of infrastructure, the more we will end up having code sending out messages. But we also want to gather some state while we are processing it. That state will be written to some storage layer. And once we're done, we want to commit that transaction. And hopefully everything that we have here is consistent. While if you're running on premises with, for example, MSMQ and SQL Server, with queuing and SQL Server insert on top of SQL Server and queuing on top of SQL Server, or MSMQ for queuing and SQL Server as a persistence, what we can say here is it supports distributed transaction. So the distributed transaction coordinator will make sure that the whole execution of this code is consistent. So what it means is that when we execute this code with support for distributed transactions, we will either have all the code executed, all the destination sends done, the storage transaction committed, and everything committed and the message being handled, or nothing, no side effect has happened. So far, so good. But if you execute this exact same code on premises and you start realizing, well, your SQL Server or your MSMQ is not actually coping with the load that you have, you need to have a higher throughput on premises, you might consider to move to RabbitMQ, for example. At this point in time, what it means is, well, Rabbit, you're not only throwing away the underlying plumbing code that we just wrote against the SDKs of SQL Server or MSMQ, but it also has larger implications of how the code might behave during runtime. What we can say, for example, with RabbitMQ, it doesn't provide you a cross-queue transaction, and it doesn't provide you DTC support. It only supports receive-only transaction. In the receive-only transaction mode, what we can say is a message receival is wrapped inside a native transaction, and once we are done with handling that message, we either NAC it in the positive case, or in the unsuccessful case, we essentially NAC it to the broker. And in this mode, the only guarantee that we have is that the message is either handled and removed from the queue, or not handled and moved back into the queue, but downstream code might be executed and partial updates might be visible. Let me show you what partial updates means. So, for example, when we have a successful write into the database with RabbitMQ, that successful write and that transaction will be committed. But if one of the destination, one other code that is executing there and wants to send out destination fails, then this might fail completely, but the entries into the storage are still written and the data is written. So that's a partial update. Or what could also happen is that we have partial send. So partial send means some of the messages that we send out might be sent, but others might not be sent. So in this case, we could have effects where we're actually not writing to the storage layer. We're sending out a message to destination 1, but we are failing to send out the message to destination 2. So what we can say for our code is that all the handlers or all the code that we're executing on the RabbitMQ with this receive-only transaction has to be idempotent. So what it means is that the result of the code that is being executed needs to be consistent from a business perspective, whether it's executed once or whether it's executed multiple times or more than once. So in that mode, the position where we actually put our code really matters. So the position where we do the sends to the destination, the position where we complete the transaction, everything like that really matters in our code. If we don't write the code in the correct way, we might and we don't have idempotent handler, then we might losing money in production. But there is another aspect. So sometimes when things go well with our code, I mean, we don't throw away business code every day, right? We evolve existing systems. We might start on premises, but then at some point we move to the cloud. So for example, for cost-effective reasons, we might say, well, our on-premise data center with RabbitMQ in there is no longer really cost-effective. We want to use something MQP, Cloud MQP, RabbitMQ hosted, or we want to use Azure or AWS in the cloud, infrastructure as a service, or potentially in the future even platform as a service. So for example, if you move your code into AWS and AWS has the SQS, the simple queuing service up there, simple queuing service also only provides you a receive-only transaction mode. But there, the implementation is actually not done by acking and necking things. The implementation is done with a mechanism called visibility time. So, and by the way, the same applies for Azure Storage Queues if you're, for example, writing code against Azure Storage Queues. What it means is once we start processing a message, the message visibility time starts counting. So if our code takes longer than the message visibility time, for example, 30 seconds, and our code might take 45 seconds, then the message that we are currently handling will automatically reappear in the queue and can be fetched by the pump. Therefore, we would be executing the same business intent multiple times and potentially processing the message multiple times. If you're using Azure Service Bus, for example, in Azure, most people don't know that Azure Service Bus provides what we call sends with atomic receive transaction mode. So what sends with atomic receive does is, if you use the SDK correctly together with transaction scope, is it provides you more guarantees and almost side effect free code in terms of the messaging infrastructure. So when you have the Azure SDK and you use the transaction scope, then what the SDK will do, it will enlisten with a volatile enlistment in that transaction scope, and all the outgoing operations will be enlisted on the current receive transaction, and it uses a thing called send via. Sounds complex? Let me illustrate you that pretty quickly. So when a transaction starts, we execute the code. So instead of going directly to the destination with messaging, we essentially send those messages back to the input queue, so to speak, correlated or attached to the current message that we are handling. So we're sending that message, setting a send via header to destination 1 and destination 2. And then we do our storage update. Obviously, that is not enlisted in that transaction. That's a different transaction. And then once we commit the transaction, what happens is the broker behind the scenes will automatically deliver those messages in a safe way to the destination queue. So this mode essentially allows us to prevent the occurrences of ghost messages. So we will not have partial sends or ghost messages when we use that mode with the Azure Service Bus SDK. So far we talked about the transactional capabilities that we have to think about when we deploy code on premises, but also when we move to the cloud. But in the cloud, there is also something else that we have to think about. Well, in the cloud, there is this concept of penny pinching. What it means is every cloud request, every broker request that we do to our infrastructure in the cloud has costs associated with it. We might have a free tier, we might have something included in a standard subscription or whatever. So for example, with Azure Service Bus, we might have 13 million operations a month included, and then we have potentially 87 million operations per month that cost us roughly 80 cents per million operation. You might think, well, that sounds like an awful a lot. I mean, 87 million is a huge number, isn't it? Well, what we can say, if we boil this down, this 87 million down to requests per hour, it gives us 120 requests per hour. And this is not really a lot, considering that every receive and every send operation that our code does will essentially be one request against the broker. And well, consider also that the code that you're writing, for example, if you're doing a naive approach of that code and the developer writes a for each loop and sends out multiple messages, then every call in that for each loop will be an n+1 problem, right? It will issue additional requests. So what we can say, in order to reduce the latency, but also the bandwidth that we have in a cloud-enabled solutions, we have to apply a batching concept. And by the way, a batching concept also allows us to reduce the number of ghost messages that we have, but that's a topic for another talk. So what we essentially do is we batch as much message requests as we can into one single call to the broker. That's batching. And I kind of hand waved, you don't see me, but I kind of hand waved and said as much as we can into a single request. But cloud infrastructure also for scalability reasons, has limitations. For example, on the Azure Service Bus standard tier, we can batch 256 kilobytes of data into a single request. AWS SQS has also 256K. If you're doing code against Azure storage queues, we can only batch 64 kilobyte of data into one single call to the broker. So we have to take message size into account. On RabbitMQ, we don't have that problem really. We can shuffle as much data as we want into a smart batching logic. We're only limited by the resources that the broker will be using the larger the messages get, and that might considerably decrease the throughput that we have in our solution. So we have to write some code that somehow figures out how much we can essentially put into one single request in order to optimize the costs in the cloud. And now we really have the basic bits, right? After all, we said it's pretty simple. We're just sending and receiving messages, and we have a little bit of transaction handling, and we have optimized the cost of our infrastructure against the cloud providers. But as we all know, when we write code, our software also grows, and the demands against the software, the business requirements also grow, and our infrastructure and library and frameworks that we write also have to essentially be evolved over time. So what we can say is we're always living on the edge of sanity, because we might get requests, well, we want to scale out our solutions. We want to do competing consumer against queues. We want to do state management. We want to have runtime configuration of our routing data that is automatically refreshed once we deploy a new client. But we also have the human factors that goes beyond the code that we essentially write. People in our team have to understand the code that we write. They are probably not experts in writing code against RabbitMQ or Azure Service Bus. We also have to have some kind of a documentation, right? If someone new joins the team and says, what is this messaging library over there? How do we maintain it? How do I use it? There has to be documentation and samples available that shows those new team members how to do it. And what happens if you, the mastermind that wrote that code, leaves the team, but because at some point you want to move on potentially to the next employer or potentially into another department where you think there is another cool project happening? Those are the aspects that we also have to take into account. But then there is also this freaking production problem, right? So we have built, we are trusting our infrastructure, we're trusting our code, we're trusting our message-based architecture, our Fireandforget infrastructure. But now we have this distributed systems mess. And how do we know what the heck is going on? How do we troubleshoot that thing? How do we monitor what is going on? How do we visualize how those messages are flowing on in the system? And even some other things, like for example, the CEO at some point in time comes to your team and says, hey, we just acquired this new company, and that new company will have a message load of 80 million messages a month. Can we handle this? Is our infrastructure ready? How do you answer those questions to the CEO? And well, if we have an outage in production, how do we know where things went wrong, and how do we seek the problems and boil it down to the code? Wouldn't it be nice if we had more insights into what's actually happening in our production system, or even in our dev test or staging system? Let me show you how an insight might look like. So for example, I have here a distributed system that contains multiple endpoints. We have a billing endpoint, a client UI, a sales endpoint, a shipping endpoint, and we currently see the critical time is potentially in good shape. So if we increase the traffic on our system and potentially if we also increase the time it takes to process a single message on our sales endpoint, what we can see then is suddenly the critical time, for example, in our sales endpoint starts growing and growing. If we dig into it, we can see that, whoa, we have a problem. Our endpoint, our sales endpoint, can no longer cope up with the message load that we have in our system. We see that the critical time is now 22 seconds. So it means that until the last message is handled, it will at least take now up to 30 seconds, and it will grow over time. And we also see how long it takes to actually process a request, and we can boil into a single message that we have and see how it behaves for a single message. And what's even better is, for example, if things start failing, and if we go back, we can see the failure rate in our system, and we can hook up monitoring solutions or alerts or triggers that shows us that something is going wrong. And even if it's just from time to time visually checking what's going on, and if we have failed messages, we also see that we have failed messages. Once the system starts essentially getting better and better, and we deployed code that actually fixed it. For example, we deployed code that fixed the sales endpoint. We can see how the system heals itself over time, and the critical time goes down over time, and we know that the things that we deployed into production actually solved the problem that we were seeing. So this is how insight into your distributed system could look like by using, for example, Service Pulse with nService Bus. Well, what I showed you here with that demo and with the code and all the explanations with Azure Service Bus and RabbitMQ, we kind of, when we started with the premise of it's super simple to write code against queuing system, how we send messages, how we receive messages, but the devil is in the details, right? So we kind of unpeeled the onion of the distributed system, and we started crying, because we realized that, well, at the end of the day, although we really like as developers to write infrastructure code, our job is to deliver business value and not to write infrastructure. So while I showed you all those basic bits and pieces that hopefully allows you to not make those mistakes that I did in the past, you have now a lot of insights what you have to think about. I think writing a robust queuing infrastructure is super complex, and you should think twice whether you really want to do it. Maybe more than twice, maybe 10 times whether you really want to do it. And I usually compare it to, it's a bit like doing a surgery on myself. While it is possible to do surgery on yourself, you could try it at home. I don't, by the way, I don't suggest it, but I mean, I would rather trust a team of professional surgeons that do surgery every day and that are specialized in that field, instead of cutting myself with a knife into my leg, for example, to do a surgery on myself and potentially bleed out while trying. Thank you very much for listening, and I hope you had a good time. And before we go to Q&A, David, let me show you a few things. So if you're curious how nService Bus works and you want to get a quick start, you can go to go.particular.net/nsbstart. That shows you a simple example how you can get started. If you're already an advanced user of nService Bus, or if you're just curious how the monitoring stuff works and you want to play around with the demo I briefly did in this talk, then you can go to go.particular.net/demo, and you can download a fully self-contained executable thing that you run on your machine and that runs multiple endpoints, including the UI, and shows you the nice graphs that we just had. And by the way, you're not limited to use what we have. You can also, for example, hook up Microsoft Azure App Insights, Prometheus, Grafana, or New Relic Insights, whatever you want to be using in production. And if you're curious about the slides, here is a link to the slides. It's on github.com Daniel Marbach /message pump. And now let's go to the Q&A, David.
All right, thank you, Daniel. The first question is, can N-Service Bus use Azure Event Grid as a transport to do push-push? This way we can avoid handlers polling the queue.
Okay, so right now Azure Event Grid is not officially supported, but we have one team member, Sean Feldman. He wrote some kind of a spike code. We can send out the link to that example, which shows how you can hook up Azure Event Grid with N-Service Bus.
Cool. Next question. It was originally fairly early in the talk before you got to the middleware. Can you bring back up the code and look at the code as it eventually was?
Here?
Yeah. The question is about, can the message pump send a message to multiple handler instances? So if you could just kind of highlight how that happens in this code.
Okay. So here in this code, well, it's a fairly straightforward implementation, right? We resolve all implementations of I-handle messages, and by the way, that's pretty much simplified. We potentially would also need to match for the message type and have some kind of a registry which filters out implementations of I-handle messages for the generic parameter t. But this is what we get, right? We get all the handlers and then we execute them all. So currently we execute them sequentially, one after each other. But we could essentially switch this code to use a task when all, and then all the handlers would be executed concurrently. I hope that answers that question.
I think so. By the way, if we answer a question and you don't think it was a good enough answer, you're more than welcome to add another question to the list. Back in the code, was waiting until message processing is finished, is that intended or not? Could you talk about some of the pros and cons to both ways of doing it?
Are we talking about the graceful shutdown?
No, I think it's like Fireandforgetting the code, the handlers versus like basically awaiting until the handler is completed before.
You mean the evolution of the first version to the first version of the pump to the that version of the pump?
Yeah, I think so. Mm-hmm.
This one which did not apply limiting concurrency. Mm-hmm. Yeah, so that was intended for the storyline, right? For this presentation, yes. So, but I mean, the only difference, like I tried to explain, between this code and the limiting concurrency is that you add a semaphore. And obviously the semaphore only limits the concurrency for one processing node, right? A semaphore here is not a distributed concurrency limiter. If you need that, there would be even more complex infrastructure you have to write. But at least we can say for an endpoint instance that we have deployed, the semaphore allows us to limit the concurrency. But then after we know that we have slots available, we don't want to await all those fetches. If we would await them all, we would essentially couple the message processing loop together with the result of the execution of a single message handling pipeline. That's probably not something we want. You might have reasons why you want that, but usually I'm not sure if it's a good idea.
All right, next question. If you wanted to handle a certain number of messages at a time, would the semaphore limitation work similarly to a thread pool?
So I'm guessing here we're talking about limiting the thread pool resources?
Probably, yes.
Okay, so well, the thing is with async await is we're no longer bound to threads, right? We're executing tasks concurrently. So while you could think that setting the thread pool limit to, for example, 100 threads might limit to execute only 100 things concurrently, that's not really true, because in an async enabled world, we're not blocking threads. So a single thread can handle multiple hundreds, even thousands of things concurrently, thousands of tasks concurrently. So limiting the number of threads might not give you the desired results.
All right, here's an async question. Wouldn't it be better to use task factory start new with long running option to create a task instead of task run?
Okay, that's a really good question. So the short answer is, in this case, no. Why? Because we use task.factory start new or task.run to offload something on the worker thread pool. I'm not going into more details about that, but since this body here of this task.run is async, what's going to happen is that when the first await statement is reached, the code, the thread that is entering that code will be released to work on other things concurrently. So when we do task.factory start new with long running option, what we're telling the TPL runtime is, hey, dear TPL runtime, we're going to execute something synchronous blocking that takes a lot of time. Please give us a dedicated thread that handles that stuff. And that is nice if we had that keyword async here. With the keyword async, what's going to happen with task.factory start new is once we reach the await statement, that freshly created background thread will be given back to the thread pool, and we're actually not winning a lot. We just take longer to bootstrap this code. Plus, there is another side effect that we have to deal with once we're using task.factory start new with an async body. The thing that is returned here is not a task, it's going to be a task of task, which is a proxy task that we have to unwrap, another potential pitfall. So in the async world, and if you want to offload something from the main thread, like a while loop, you're better off using task.run. It's the safer API.
All right. So the asker says this is an off-topic question, but I'm not really sure that it is. Can we have multiple endpoints hosted on the same handler Windows service? If so, what are the limitations of hosting multiple endpoints in one Windows service handler?
It sounds like a specific end-service bus question. I'm not sure. Or, I mean, if you talk, for example, about end-service bus, yes, you can have multiple endpoints hosted in the same Windows service, definitely. The limitations are you have to set up assembly scanning in a way so that only things that are relevant in the current app domain for a specific endpoint get scanned. But we can, David, I think we can note down this question and also send out some further links to our documentation samples about multi-endpoint hosting.
Yep, I think that's a good idea. I think that's actually all of the questions we have time for. So I know we have more questions. They are very broad questions, though, that could deserve a webinar all on their own. So I think we'll try to follow up with those individually or maybe with blog posts or other resources in the email.
Mm-hmm. Cool.
All right. Well, thank you, Daniel. This has been another particular software webinar, and we will see you next time.